This isn't a fancy video. It's just so that I can quite quickly talk through the proposed modifications to the JSA slides as we discussed them last Thursday. And I can talk a lot faster and say a lot more than I can when I try and write. I suggest that we add the slides, we make the modification in this section that talks about understanding hazard recognition. So it falls still in the same storyline, falls in another section. It is just focused on trying to give people the skills to see things in the workplace and to be able to think about them. The idea is to wake up their mind, to make them think a little bit about the things that we become industrially blind to. We give them the idea or the mission of the section, and we say the idea is to identify hazards, to find them, then to be able to assess them, analyze the hazard, evaluate the risks, which comes later on in the section, but that's all part of this whole exercise that we are engaging in for the job safety analysis, and then to be able to fix it, put preventative and mitigating controls in place so that people do not get injured. I've changed the old picture. That's a shutter stop picture. I've got a list of audio-visual parts of the slides that we will look at before we finalize the presentation and to buy them whenever we can. This is a person welding inside a tank, and I think it's fairly applicable to the environment that we will teach in. And the idea is to say, okay, guys, you tell me what these hazards are. And I want to hear about the tank, the welding machine, the cable, and then hear about UV radiation, potential vapors in the tank, maybe liquid in the tank, overhead environment, and so on. Here's another picture, also a stock picture that we could look at buying. And the idea is to make these guys aware that I'm not looking for the rules that are being broken. I'm looking at, they must identify the pipe, the fan, the overhead crane, the person sitting here painting, the angle grinder, some equipment in the background, the structure of the building. Those are the hazards that we're looking for. I'm not looking for rules that are broken, bad housekeeping and that kind of stuff. Similar kind of setup. These are just options that we could look at, and maybe you have some other items or pictures in your company that might be more suitable. Here I want to hear that there's a crane, excavator, there's a pipe, there's a ladder or theodolite, there's an angle grinder, another angle grinder, a pallet, a tractor, and so on. What we want to illustrate to people, and what we will do is when we do these exercises, we'll take them through a picture, and then we'll compare notes. What did they see and what did they miss? And the idea is that they need to come to some kind of an awareness that if you can't see the hazard, somehow it's going to get to you later on, because you can't identify it, so you can't get information on it, you can't understand it. If you don't understand it, you can't control it, and then it hurts you. I use the same definition for a hazard from the IOSH that you have, and we just highlighted what is a hazard, what is a barrier, what's a control, what's energy. This comes straight out of Bill Haddon's and the hazard barrier energy models on which things like the bow tie has evolved. I'm not too hassled whether it's a barrier or control. Typically, a barrier is a hard construct, whereas a control is something like a SOP. We don't have to complicate things. A barrier is anything that will stop that hazard from contacting the target. We'll get to that in the next slide. When we talk about energy, now a guy like Jim Joy when somebody made him aware, Professor Jim Joy of the University of Queensland, He came with a very academic approach, and he came back and he wanted people to identify energies. Now, the poor soul on the job cannot even identify a chemical canister and a piece of equipment. Now you want to now you want him to identify energies. Professor Joy also had a misconception, in my opinion, well, not in my opinion, according to definitions, where he didn't say a hazard is a hazard and it stays a hazard whether it's in control or not. He said that a hazard is only a hazard if it's not in control, which is not true, because that only increases the risk or decreases the risk, the amount of control on the hazard. A hazard is a hazard is a hazard. Whether it's a small lion or a big lion, it remains a lion. If it's a small hammer or a big hammer, it remains a hammer. That's the concept that we're pushing through. Now, I put together a bit of an animated slide which demonstrates the relationship between the hazard, the energy flow, the target, the event that takes place, the barriers that are mitigating controls, the evolution of the event after, and the preventative control. This is in line with the latest move where organizations are increasingly moving towards using bow tie analysis to demonstrate this relationship. It makes it easier for people on the floor to see this relationship between the hazard, a pathway, and so on. But let me go through the slides and you'll see. So we start off with the concept that we've got a hazard, and a hazard has got energy. A hazard needs that energy to be able to effect a change, do work. If the hazard hasn't got energy, it can't do any useful work, can't do any harmful work. So a hazard must have closing potential and it must have energy. Hazard is anything physical that you can hear, see, smell, taste, and some of the things you can't even see and taste and smell. We'll get to that in detail as well. The other role player in this matter is the target. The target can be production, can be financial, can be reputation, can be people, can be machinery. And for this hazard to be able to do harm on the target, the energy from the hazard needs to be transferred. So there's an energy pathway. We put barriers in to protect the target from the hazards. And normally the first barrier is the primary containment of something. For instance, if the hazard here would be a pressure vessel, then the design and construction of that pressure vessel by the manufacturer and the valve would be such that it would not easily break down or explode and hurt people. They design it in such a way that it is safe. That's the first barrier. That first barrier has to be corrupted or broken, or it has to fail in order for that energy to be able to flow to the target. In other words, a valve has to fail, a PSV has to fail, a vessel has to rupture. Something has to fail for that gas or the pressure to be released. Following that, the target may be affected. We also recognize nowadays that before I get there, we know that if that energy gets released, then there will be an event, an incident. The magnitude of that can vary. That's part of risk. And the likelihood of that event is related to the controls and the barriers. So that's risk, and we'll get to that later. If the event takes place, there are various end scenarios. And this, if a pressure vessel ruptures and there's pressure or shrapnel that impacts on the target, there can be several outcomes, depending on luck, basically, and on conditions and so on. And the person, nothing can happen. There can be no harm, or we can end up with an injury, or we can end up with a fatality. We don't have control over which one of these paths in most cases, because we've given up our control in the preventative steps. The latest evolutions of the old hazard barrier target model, which we've seen so far, works in complicated systems, and that's why nowadays when we produce these failure models, we use fault tree analysis, event tree analysis, and those kind of things, and that's where the bow tie, of course, comes from. So this side would be a fault tree analysis with multiple causes, multiple primary barriers that could fail. So there are many pathways by which this pressure vessel could eventually harm the target. A valve can fail, leading to a gas release. A pressure safety valve can fail, leading to overpressure in the system, ruptured vessel. The pressure vessel can fail, causing material to fly all over the place and shrapnel hits a person. If the pressure is let out and it impacts on a person, he can suffer from air embolism and so on. So multiple paths by which this energy in the hazard can actually impact on the target. What do we do to control this energy flow? Once we understand how this hazard can behave and the characteristics of this hazard, we can block the pathway of energy on the way. We do that through mechanical means, barriers, separation in space. We write rules and procedures. We address safe behavior so that people don't go into the area. We have isolation and so on. But we can only put effective barriers in place once we know where and how that energy can possibly flow to the target. If I miss one of these pathways, if I miss one of these arrows that is getting shot towards the target, then there's a very high chance of that hitting the target, and then I have an event. We call this preventative controls. It prevents this event from occurring. Then once the event occurs, we need to mitigate the controls. We might have alarms, evacuation. We have PPE. PPE is not a preventive control, it's a mitigating control. Only protects you once an event takes place. So we put these mitigating controls, emergency response, PPE, firefighting, first aid, all of those kind of things. And all of these things together will determine whether or which of these scenarios we end up with. Are we ending up with a huge toxic gas release with multiple people dead, or are we going to end up with a small gas release or a small fire, first aid case, injury where we save the guy before he dies on the way to the hospital, or if he gets killed? Confined space incident as an example, if my mitigating controls are good, I can actually still save a person even if he's asphyxiated in a confined space area. If I don't have good controls, then more than one person enters that confined space and we end up with a multiple fatality. So this whole picture, this whole description is there to talk about this relationship. And we can talk, there's a variety of examples that we can use: confined space entry, pressure vessels, working at height, all of these hazards we can discuss along these lines. This is again a discussion that we have in the class now that we've gone through the relationships. We get people to identify the hazards. We get them to identify how the energy may get transferred, and then they must tell us how will this energy get transferred so that you will actually prevent it from hitting the targets. Here's another picture as an example. In this case, some of the hazards are not visible. They might be inside this container, inside the pipes, and only when the primary barriers go astray or we start opening these vessels do we then get the event. Now we get to some of the practical aspects of what is a hazard in the workplace and how do we actually see it. Everything that you can detect with your senses is a hazard. Anything you can see, smell, hear, taste, so on. You don't want to taste everything, but you should. That is applicable for 80 or 90% of the issues. We say that a hazard requires energy to close the gap between the hazard and the target and to be able to cause harm or useful work. All hazards contain energy in some form. Energy is the ability to make a change, to do work. If a hazard has got no energy, it's no danger to us. If you get up in the morning and you don't have the energy to get out of bed, there's not a chance that you're going to be fighting your enemy later on today. Energy is useful if we use it in a controlled fashion, but it's harmful if it just gets out in an uncontrolled fashion. Energy can cause serious harm if it's released in a harmful fashion. But we have to be reminded that hazards are physical objects. The moment that I start talking about the chance of something being there, then I'm talking about risk, because risk is considering the likelihood or the chance of something happening associated and the consequence if it does happen. So if you start talking about anything, you say there's a possibility that something, then you are talking about risk. You're not talking about a hazard anymore. If you're talking about the possibility of a hydrocarbon being in a heat exchanger or in a pipe or being, the hazard is the stuff that is going to get out. The possibility of something happening or you getting exposed to that is the risk. Some hazards, I said 90% of the stuff you can detect by your senses, but there are odorless gases which are toxic. There are colorless gases, and they are fatal. CO2, nitrogen, those things are colorless, odorless, but you can detect their presence through some kind of a device. Pathogenic substances, bacteria, viruses, some of those things, Legionella, all of those kind of bacteria and things, they are still physical things. They are just so small that you need to use a microscope to be able to see them. And you need to be able to use a gas test or something like that to see the gases that you can't sense. Also, some of the hazards might be present, but you don't see them immediately. They might be hiding in pipelines, in vessels, in containers, and other stuff, in sumps, in sewers, and those places. So you can't see them immediately, but you've got to be able to identify where this animal, where this danger lies, where it lurks, where it hides. And if you can identify that something like that might be present, and it will likely lurk or sit in that cavity or live in that cave or in that pipeline, you are already on the way to proper hazard identification. Now, currently in the SABIC classification, you guys have classified the hazards, I think, in 5 categories. We can still go with that. I don't have an issue. This is just another slide. We break down the way in which energy, it's not really energy, because there's only really 3 kinds of energy, but we talk about energy sources or types of energy sources, or maybe types of hazards, which gets their energy from electrical properties, mechanical properties, chemical properties, radiation, and here we talk about UV, IR, but also radioactive radiation. We talk about sonic noises, low frequency, high frequency, thermal heat, once again infrared heat, hot surfaces, nuclear, kind of ties up with a nuclear radiation up at the top, pneumatic actions, pneumatic forces, hydraulic, and there might be others as well that we haven't covered. An important thing that people need to understand is that some of these hazards, it's not, like I've already mentioned, it's not so easy to see them and to identify them as a source of energy, because in many cases they don't act as a like nitrogen, doesn't act on the person to do harm to them, but it acts by excluding something that it requires, taking away the oxygen. But when I use something like argon to treat, then it's once again it's a colorless, odorless gas. But in this case, the gas actually acts by producing chemical burns in my lungs. Pathogenic organisms, not always so easy to see that it's energetic and that it does energy, but it cannot do any harm if it doesn't have energy. The next slide tries to highlight the fact that even though a single hazard, let's say the wind, is not that strong, so it's not a big issue, but suddenly I am lifting a big steel plate. And because of the area of the steel plate and the medium force of the wind, now I have an issue. Also, if I have fuel or fires or flammable materials and a heat source, and I add wind to it, then suddenly the hazards working together become have a greater effect. They present a greater danger. Things like electrical discharges or other ignition sources, static electricity, equipment that are not well maintained, things with hot sources combined with flammable and explosive gases, chemical interactions, putting two different chemicals like, for instance, nitric acid and organic materials, putting those things together, oxidizers, fuels, fertilizer with fuel material, can actually greatly increase the effect that a hazard might have if it's acting alone. So once you see these hazards, you also need to look at interactions between them. Then we're looking at explosions, and an explosion can cause damage in terms from sonic noise, a blast, pressure wave, and also thermal radiation. So the effect can be multiple. It's not just in a single dimension. Once we've gone through that theory or that introduction, and we talk during that session, we'll talk with each other and we will hear the people's opinions and what hazards they can contribute as we go along. And then we need to go through a bit of a practical exercise. We divide up into groups and we give them a form like this and say, okay, you already can visualize your workplace. List the stuff that you know already exists in your workplace. You don't see it right now, but you've been there every day. So list the hazards, and I want to see that they're actually getting to the point where they list the hazards, where they can identify the energy flow, and whether they can see the events and the consequences. This is your slide where it's the classification of the hazards. We may need to discuss whether we expand it with the one that I suggested or whether we just go with these categories to keep it simple. I have no hassle either way. Now we go into the practical application of the skill and we say, where do we get the information from to do this hazard identification risk assessment? And we can get information from ourselves, from our own knowledge and experience. We can get it from other people. We can get it from literature. We get it from experimentation, although experimentation can be dangerous, so that is not recommended. And we get it from history, past incidents, and our own mistakes and successes. So we can zoom into areas. In other words, instead of looking at a big project, we only focus on one job, one task at a time, and we focus on this area so that the items in this area stand out bigger. We use multidisciplinary teams so that we get the input from a variety of people, and we want to discuss. That's why we do risk assessments in groups and hopefully under an experienced facilitator. This is the Abbey that we discussed. It's an additional looking tool where we tell people you enter the area, come to the workplace, and then you look above you, below things, behind things, and inside things. Then we move on to analyzing the hazards trying to get people to think systematically, not just, well, firstly, we're trying to get them to see things. And then we need to get them to think about the things that they see. So here we say, is something large or is it small? Is it heavy or is it light? What is the density? Is it lighter than air, lighter than water, heavier than water or air? And we go through this whole exercise. And then we discuss that the characteristic of a hazard is not necessarily a bad thing. In other words, if a box is light, it's a good thing. But if the box is light and it is very large, then it can occlude your vision. You can't see where you're walking. So it might be light to walk with and good from an ergonomical point of view, but it's bad for avoiding obstacles and so on. Mass, sometimes you need things to be heavy to hold them down, and if it's not heavy enough, then that creates the risk. Sometimes if you want to carry things, it shouldn't be so heavy. So we talk about these characteristics and talking about whether they are good or bad depending on the scenario, depending on the circumstances. And in the end, it still gets back to energy transfer. So it doesn't matter whether it's big or small or round or smooth or edged. It's about how will this thing transfer energy and what will be the consequences of it. Now, there are some limitations to this method that I've just described, the walking around, the zooming, and so on. And one of them is that some hazards may go undiscovered because you can't see them because they're colorless, odorless. You don't know where to expect them. They are hiding inside vessels, but hopefully we've built in some mechanisms to address that. If an operator is overburdened, if there are too many places that he needs to see, I'm thinking of people that are permit issuers and there are multiple permits that they need to issue and contractors and they don't have the time. That is a problem. Negative static stability margin, not an issue in this application. Also, some of these controls that we are going to put in place, it's not so easy to put them nicely in a box. Surge protectors or vaccines or self-containing breathing apparatus. It on the one side for confined space entry, self-contained breathing apparatus is a control. It gives you the air, but it's also something that limits your movement, can stop you from getting into and out of places if you need to quickly and so on. These are your slides, just shows where we end. We then talk about the hazard contributors, the things that helps these hazards, or that the things that we're supposed to do and we don't do them, that eventually allows these hazards to still get to us. The contributors that helps these hazards create these events. And then that is the end of the proposed modifications.